Okay, good evening, good morning, good afternoon, wherever you are. Welcome to our colloquium. And today we have Monica from the Department of Mathematical Sciences, University of Memphis. And she will give a talk. The title of her talk is Numerical Index of Banach Spaces. Over to you, Monica.
Thank you. So as Dr. Sudeshna said, today I will be talking about numerical index of Banach spaces. Thank you all to be here for taking out time from your schedule. I hope this talk will be interesting to you. I will start from very basic and build up the concepts, but still, if in between, if you don't understand anything or there is any gap, just stop me there and ask me questions. So let's start. So let's see the overview of this talk. So first we will see some notations we are going to use in this talk. Moving forward, we will see some preliminaries. And then towards the end of the talk, we will talk about the numerical index of LP spaces. Let me know if at any point you think I'm going slow or fast. So let's start with the notations. Throughout this talk, H will denote the Hilbert space. For Banach space X, X star will denote the dual of X. Bx will denote the closed unit ball. Sx will denote the unit sphere. By Lx, the script Lx, we will denote the Banach algebra of bounded linear operators on X. And for any bounded linear operator T, T star will denote its adjoint. By co-B, we will denote the convex hull of B, and by this bar, we will say it's the closure. So this is closed convex hull of B. By sigma T, we will denote the spectrum of operator T. And by script K, we will denote the scalar field. If I'm going to use any other notations other than that, I will mention at that point only. And if still you are confused about any notation, please feel free to ask. So in 1918, Topliss introduced the notion of numerical range for matrices. He defined the numerical range of matrix A as the inner product of Ax with X, where X is norm 1 vector. But this definition applies equally well to the Hilbert space also. There is little lag between when I change the slide and when it appears on your screen. So let me know if you have some more disturbance. So for infinite dimensional Hilbert space, numerical range was defined as same as the matrices, the inner product of Tx and X, where norm of X is 1. So what is the importance of studying the numerical range? The numerical range actually gives us a nice picture of the operators, which allows us to see many geometrical and algebraic properties. It will be more clear when we will be discussing about the properties of numerical range. And also, it is a comfortable way to study the spectrum of any operator. Throughout this talk, I will be talking about bounded linear operators. Also, numerical range is a good way to work with Hermitians and skew Hermitian operators. So let's see some properties of numerical range. The set, so numerical range is basically a set. This set is a convex set. WT is always a convex. Remember, we are on Hilbert space setting. So when we are talking about numerical range of an operator on Hilbert space, WT is convex. Moreover, the spectrum is contained inside the closure of numerical range. It means we can get the bound of spectral radius easily if we have the knowledge of numerical range of that operator. Also, if T is normal, the convex hull of spectrum coincide with the closure of numerical range. Means in that case, we can, if we have the knowledge of numerical range of operator, we can talk about we can easily find out the spectral radius. If alpha and beta are scalars, then numerical range satisfies the property that the numerical range of alpha t plus beta s will be contained inside alpha times numerical range of t plus beta times numerical range of s. And if we replace t by identity and beta by 1, this inclusion changes to equality. Means the numerical range of alpha I plus s is alpha plus numerical range of s. And the numerical range is invariant when multiplied by right hand side a unitary operator and left hand side by the adjoint of that operator. Numerical range of u star tu is same as numerical range of t when u is unitary operator. So next very general thing is we want to extend the notion of numerical range to general Banach space. And it was done by Lermer and Bure in 1961 and 62. They introduced the concept of numerical range to general Banach spaces. They defined the numerical range of a bounded operator T as Vt is x star Tx, where x and x star are unit vectors satisfying the property x star x is 1. So this numerical range is set of all points x star Tx, where x and x star are unit vectors satisfying x star x equals 1. Now let's see some properties of numerical range when we are working on journal Banach space. If we are on journal Banach space, Vt is connected, the numerical range is connected but not necessarily convex. Remember, when we are working on Hilbert space, the numerical range is convex, but in Banach space setting, it's connected but not convex. And uh, a, a very easy to see after it was done, but very hard to construct example was given in the book. So let me show you this book. So this book is Numerical Range. There are two parts, 1 and 2. It's by Bonsall and Duncan. These two are like really nice books to start. They have really good examples also. So this example I picked up from that book. So in that case, we define the norm like this, and we take an operator T whose matrix representation is 0, 1 over 3, 1 over 3, 1. In that case, it was seen that if we compute the set of numerical range, it's actually two teardrops joined by a length segment. Means it will look something like this. We have a line segment and then two drops like this. Something like this. So it's connected but not convex. Same as the Hilbert case setting, the spectrum will be contained inside the closure of numerical range. And numerical range will satisfy the property that alpha t plus beta s is contained inside alpha times numerical range of t plus beta times numerical range of s. But if we replace t by identity and beta by 1, this inclusion turns to equality. A numerical range is invariant when we multiply by right-hand side a surjective linear isometry and left-hand side by its inverse, which means numerical range of U inverse TU is numerical range of VT when U is surjective linear isometry. And the numerical range of T is contained inside the numerical range of T star, which is contained inside the closure of numerical range of T. And this is like an important property. So let's calculate the numerical range of an operator just to have a little bit of idea. So I am considering this operator T whose matrix representation is given by 0, 1, 0, 0, and we want to compute B of T. Just by the definition, it's x star Tx such that norm of x is 1, norm of x star is 1, and x star acting on x is 1. So if we compute Tx, which is 0, 1, 0, 0, acting on x1, x2, we will get x2, 0. Now, if we compute x star Tx, we will get x1, x2. So this set Vt is nothing but x1, x2 such that x1 square plus x2 square is 1. More to that, we can say it's x1 square root of 1 minus x1 square when x1 belongs to 0 to 1. This was a very simple example to compute the numerical range of an operator. Next, moving forward, we will talk about numerical radius. I'll interrupt you in between. When I was writing on the board, were you able to see it?
Yes, we could see it. Yes.
So next I'll talk about numerical radius of a bounded linear operator. So when we were talking about numerical range, side by side we considered the spectrum. So when we have a spectrum, to find out the spectral radii, it's the supremum of absolute values of elements coming from spectrum. Similarly, numerical radius is supremum of absolute values of elements coming from numerical range. So it's nothing but supremum of elements coming from numerical range, which were x star tx. I'm writing the definition again and again so that you can, like, if you haven't seen it before, it will be easy for you to recall. So the numerical radius is supremum of absolute value of elements coming from numerical range. Let's see some properties of numerical radius also. So the elements are of the form x star tx. It's in absolute values. So Vt for any bounded linear operator will be greater than 0. And using the triangle inequality, we will say it's less than norm of t, because norm of x and x star is 1. So Vt will always lie between 0 and norm of t. This V actually is a semi-norm, which means Vt equals 0 doesn't necessarily mean that t is 0. Also, the supremum of absolute value of sigma t will be dominated by the numerical radius of t, which means the spectral radius will be dominated by the numerical radius. And if we multiply right hand side by the surjective linear isometry and left hand side by its inverse, then the numerical radius is invariant under such multiplications, just like the numerical range. But the important property in this case is the numerical radius of t star, the adjoint operator, will coincide with the numerical radius of t. In the case of numerical range, we had it's contained inside. The Vt is contained inside Vt star is contained inside the closure of Vt. Here we are taking the supremum, so these coincide. Okay. So let's compute the numerical radius of the operator we talked before, 0, 1, 1, 0. So we know the numerical range already. It was x1 times square root of 1 minus x1 square, where x1 belongs to 0 and 1. So this time we need to calculate the supremum when t belongs to 0 and 1, t times square root of 1 minus t square. Now this is function of one variable, and we can easily find out the supremum by calculating the derivative, see where the supremum attains, and you will see that the supremum is 1/2. So the numerical radius of this operator is 1/2. Now if H is Hilbert space, there exists a bounded linear operator T whose norm is 1 and the numerical radius is 0. Whereas if H is complex Hilbert space, Vt will be dominated, the lower bound will be 1/2 times norm of t. And this 1/2 is actually the optimal constant. Means there exists a Hilbert space and operator t such that Vt will the norm of Vt is actually 1/2 norm of t. For spaces like L1 mu, Ck, Vt will coincide with norm of t for every operator t. Okay. Moving forward, I will start with numerical index. So numerical index of a Banach space is a constant. So till now we were talking about the operator. Now numerical index is related to the Banach space. So numerical index is a Banach space which relate the norm of an operator with its numerical range. That's our numerical index. So let's define numerical index. Numerical index is actually the infimum of Vt where norm of t is 1. So infimum of all the numerical radius of norm 1 elements. The next definition is nothing but just the reformulation of it. Infimum is the greatest lower bound. So we are taking the maximum of all the lower bounds. So numerical index is infimum of numerical radii of all non-1 operators. If numerical index is 1, it means Vt will coincide with norm of t. Previously, we talked about in case of L1 mu and Ck, numerical radius coincide with norm of t. It means the numerical index is 1. This actually follows easily from the definition only. And if the numerical index is positive, strictly greater than 0, V, which was a semi-norm, will be a norm and it will be equivalent to the usual norm on Lx. And in general, the numerical index of dual is always less or equal to numerical index of X. So we want to know when this equality achieved. So if X is reflexive, means X double star is same as X, in that case we will have numerical index of X double star is less than numerical index of X star using this property, less than equal to numerical index of X using the property again, and since it's reflexive, we will say it's numerical index of X. So in case X is reflexive, numerical index of X and X star coincides. Also, if the numerical index of X star is 1, if the numerical index of X star is 1, the numerical index of X star and X will coincide because it's very clear that numerical index cannot be greater than 1. Vt is always dominated by norm of t, and in case they coincide, the numerical index will be 1. So the maximum possible value of numerical index is 1. So in case numerical index of x star is 1, numerical index of x and x star will coincide. The next conjecture was, is the numerical index of x and x star always coincide? And this was answered negatively. And the example was given by Bokoyo, Cadet, Martin, and Werner in their paper. They constructed a Banach space X. So C is the space of convergent sequences. They constructed the Banach space X, where x, y, z is coming from C infinite sum C, and the sum of limit of x, y, and z was 0. So in that case, they observed the numerical index of x is 1, but the numerical index of x star is less than 1. So this is the example where numerical index of x star was strictly less than numerical index of x. So the next open question is, when does the numerical index of x and x star coincide? Like, what is the necessary and sufficient condition? Also, let's see numerical index of some more spaces. So if we have a Hilbert space H, the numerical index will be 1/2 if H is complex, and the numerical index will be 0 if H is real. And it was observed by Glickfeld in 1970 that the numerical index, so here H was our Hilbert space, now we are in Banach space setting. So in complex Banach space, it was observed that the numerical index is dominated, like the lower bound is 1 over E. And he actually find out an example also where the numerical index of the Banach space was 1 over E. Means this 1 over E is the optimal constant. Later in 1970, Duncan, McGrath, Pierce, and White proved that the set of numerical index of complex Banach space is the interval 1 over E to 1, which means if you take any point between the interval 1 over E to 1, there is a complex Banach space whose numerical index will coincide with that point. And for the real case, the set of numerical index of real Banach spaces is the interval 0 to 1. And actually they constructed an example of two-dimensional Banach spaces. Like if you have any point between 0 to 1, there is a two-dimensional real Banach space whose numerical index will coincide with that point. Similarly, in the case of complex Banach space also, if you take any point in the interval 1 over E to 1, there is a two-dimensional complex Banach space whose numerical index will coincide with that point. Let's see some more examples. The numerical index of space L1 mu, where mu is positive measure, is 1, as I discussed previously also, because we saw that Vt is same as norm of T for every non-null operator. So the numerical index of L1 mu will be 1. The numerical index of CK space where K is compact Hausdorff is 1. If we are working with the C star algebra, numerical index of the C star algebra is 1 if A is commutative and 1/2 if A is not commutative. The numerical index of von Neumann algebra is same as the numerical index of its pre-dual if the pre-dual exists. And for the function algebra, the numerical index is again 1. And if we have a subspace, a finite dimensional subspace of C01, its numerical index is 1. So this is kind of like a small list of spaces for which numerical index is known. And there are like lots of open spaces for which we don't know the numerical index and we are still looking for it. Some examples of this list are CM01, the m times continuously differentiable functions, Lipschitz functions, or Lich space. The list is like very long. So the numerical index of these spaces is still unknown. But one of the most important classical Banach space whose numerical index is unknown is the LP space for P not equal to 1, 2 and infinity. For 1 with 1 and infinity, the numerical index is 1. For 2, it's Hilbert space and we know the numerical index of a Hilbert space. So to find out the numerical index of LP spaces other than P other than 1, 2 and infinity is still an open problem, and it's an open problem from very long time. Some progress is made to this problem. So towards this problem, Ittari and Kamasi in 2005 and 2006 presented some results saying that if P is between 1 and infinity, the sequence of numerical index LPM is decreasing. By LPM, I mean we are taking m components instead of infinite like we do in LP. We are taking m tuples only. So the sequence of numerical index of LPM is decreasing. And the infimum of this sequence is the numerical index of LP and numerical index of LP01. And the bound for NLP2 for m equals 2 were given. So if P is not equal to 2, NLPM is greater than 0, it's known. It means the numerical radius of operator T is positive for every non-null operator. So we know that every element in the sequence NLPM is positive. But the numerical index of LP is actually the infimum. It is possible that all the elements are positive, but the infimum is 0. So the next question that was asked is the numerical index of NLP positive for P not equal to 2? And it was proved by Martin, Mary, and Popovo in 2009 that numerical index of LP mu is always positive for P not equal to 2. And the MP we are talking here, and we mentioned the MP in previous slide also, is actually the numerical radius of the matrix 0, 1, negative 1, 0 in the real case. So now what we want to focus on is, what we want to do is, we want to somehow uh, move towards the numerical index of LP spaces, right? For that, let's first see some definition, the absolute and symmetric norm. So if we have a norm from R2 to R2, we will say it's an absolute norm if norm of 1, 0 and norm of 0, 1 is 1, and norm of AB coincides with the norm of absolute value of A and absolute value of B. And we will say that this norm is symmetric is norm of AB is same as norm of BA. And the most important example of absolute and symmetric norm is our LP norm on R2. So the computation of two-dimensional case, so to find out the numerical index of LP, see here, the numerical index of LP will be given by the infimum of numerical index of LPM. In particular, we are first trying to compute the numerical index of LP2, means M equals 2. So the computation of numerical index of NLP2 is our first step towards the computation of numerical index of LP space. But actually, this is the most important step. Why? Because it's very reasonable to expect that the that the sequence numerical index of LPM is a constant sequence, as it happened in the case of 1, 2, and infinity. But we still don't know if this sequence is going to be open. So it's still an open problem that the sequence of numerical index of NLPM is constant or not. But it's reasonable to expect that this is constant. So in that case, in that sense, the computation of NLP2 is the most important step. Okay. So let's move a little bit towards that. So we are considering X as R2, and I1, I2, I3, I4 are the onto isometries which form a basis for the space of bounded linear operators on X. Just to recall, MP, which we discussed 2-3 slides back, MP is the numerical radius of this I4 matrix. This MP is actually very important for us. That's why I'm just recalling it again and again. This MP is numerical index of this I4 matrix 0, 1, negative 1, 0 in the real case. And for P equals 2, NLP2 coincides with MP. So the next question that was asked was, is NLP2 will always coincide with MP, like for all P equals 1, 2, and infinity? Remember, we are in real case. We are talking in real case only. So our question is the numerical index of NLP2 same as MP for all p between 1 and infinity. A recent progress was made by Mary and Curo. They published a paper in 2020 only, actually. So for the for p between 3½ to 2, they proved that this numerical index of LP2 will coincide with MP. So for that, there was an important lemma that if we are working on absolute and symmetric norm, then x star I for x is a lower bound for x star ij of x when x and x star are unit vectors satisfying x star x equals 1. Just to recall, when we are working with numerical range, numerical radius, we are interested in looking on the vectors which are norm-1 vectors and satisfy x star x equals 1. So they proved that x star ij of x, the lower bound is x star I4 of x. And this is the reason why MP is coming again and again. The MP is associated with this I4 matrix. It was the numerical radius of this I4 matrix. And one important theorem they gave was, if we can find a x naught, a unit vector x naught, and a unit vector x naught star such that the absolute value of x naught star I4 of x naught gives us the numerical radius of I4, and we define Cj as the absolute value of x naught star ij of x naught for j1, 2, and 2 and 4. In that case, if C4 is 0, numerical index of the space will be 0. If C4 is not 0, if C4 is positive, in that case we will get the lower bound of numerical index, and the lower bound will be given by minimum of C4 and 2 over 1 plus 1 over C2 plus 1 over C3 plus 1 over C4. More to that, if the quantity C4 times 1 plus 1 over C2 plus 1 over C3 is less than 1, less or equal to 1, the numerical index of x will coincide with VI4, which is our MP. So this moreover part was used by them to prove for the range P between 3½ to 2. So the most intrinsic part over here is we need to find out a x naught and x naught star from the dual such that VI4 is the absolute value of x naught star I4 of x naught. This is most tricky part. Using this theorem, we can find out the numerical index of sum of two-dimensional LP spaces. But as I said, we need to find out x and x star such that x star x is 1 and x naught star I4 of x naught coincide with VI4, which is very tricky. So what they did is, so they used parametrization and they proved that this quantity C4 times 1 plus 1 over C2 plus 1 over C3 is less than equal to 1 for all t. Means for all x's for all norm1 vectors, they proved that this quantity C4 times 1 plus 1 over C2 plus 1 over C3 is less than 1 for the range they were dealing with. So for the range between 3/2 to 3, they proved that the numerical index of LP2 coincides with MP. And they proved this saying that this quantity is less than equal to 1 for all norm 1 x's. What we tried to do, I with Dr. Bento, what we tried to do, instead of looking for all such x's, we tried to work with that particular x naught. We tried to prove this for that particular x naught. So we extended the range of p a little bit. This p actually, this is actually the range of p was p between 1 plus alpha naught, where alpha naught was a zero of a function. But just to make it simple, just not to scare you, I just wrote this range because the zero of that function was very near to 0.4547. So for the range p between 1.4547 and 3.19925, we proved that the numerical index of LP2 coincides with MP. And I don't know how much time we have left. I'll just give a little sketch of this proof.
We have about 10 minutes.
Oh, okay, then we have sufficient time. So I'll just give you a rough idea of the proof. So we defined a function gt, and this function is not like a crazy function. It's not like we slept one day and when we woke up we got this function. No, this function we got like, if you will see the proof, it's very easy to see why we defined this function in such a way, because we will parameterize. And since we are looking at this, the maximum value of C4, you will put C4 prime t equals 0. And from there, you will be able to relate why we defined gt as this function. So we defined gt as this function, and we observed that this function gt is increasing. And if t tends to 0, this function gt actually approaches to 0. And using these information, we were able to prove that the value of g at the point p minus 1 power 1 over p minus 1 is greater than p minus 1 for the range 1.4547 to 2, when p is in this 1.457 to 2. And we proved, and then moving forward, we proved if p is in this range and C4 prime t is 0, then t, the t naught where the supremum is attained, will be less than p minus 1 power 1 over p minus 1, which will show us that the numerical index will be MP. But here we are working on 1.4547 to 2. For 2, it's a Hilbert space, and we already know the numerical index. And for LQ, since we know that numerical index of X star is equal to numerical index of X when we are working with reflexive space. Here we are working with the reflexive space, so the numerical index of LP2 will coincide with MP in the range 1.4547 to 3.1925. So this was about the real space. Let's see some similar setting in the complex space. So in the complex space, the I4 we are dealing with till now, if we see L22, the numerical radius of VI4 will coincide with the norm of I4, and therefore the numerical radius is not minimum. So in case of L22, this failed, the conjecture failed in the complex case. Now we are in complex case. But actually it was observed that the numerical index of L22 is half, because we are in because it's a Hilbert space, it's a complex Hilbert space. For complex Hilbert space, the numerical index is half. For real Hilbert space, the numerical index is 0. So the numerical index is half, and the numerical index coincides with the numerical radius of the shift operator 0010. So in the complex case, the question is the numerical index of LP2, still in 2 dimension, coincides with the numerical radius of the shift operator, which is given by 1 over p to the power 1 over p and q to the power 1 over q, in the case when p is between 1 and infinity. So this is still an open problem. I hope you have enough open problems for today, and if you need more, we can discuss more. I have lots and lots of them. So thank you so much for your kind attention and your time.
Very, very nice talk. Excellent talk, Monica. Really enjoyed it. Any questions, comments from the audience? Any questions, anyone? If no one has questions, I'll just like to ask a few things, like about the numerical index of a Banach space. How do you compare the numerical index of a subspace and a bigger space, for example? Is there any comparison possible? And specifically, for suppose if we have an M summand, for example, can we say anything about the numerical index of the M summand and the bigger space?
I'm not sure.
Because I recall one result where I think you said that the numerical index of the double dual is less than the numerical index of X, right? And then you had
Index
equality.
of X star is always less than numerical index of X.
And also, so numerical index of X star star is less than X. So that is why I was wondering if we can have something like that between the subspaces, as specifically if we have nice subspaces like an M summand or things like that.
What I know is if we have like the direct sum, so for the different direct sums, the property is different. So I cannot like recall for it was for C0 sum or L1 sum, but it's dominated by the infimum of the individual numerical radius, so the numerical index.
So the numerical index of the space is dominated by the infimum of the components.
Yes, yes.
Okay, yeah. That's what I was thinking when I saw this result, that it should be in the reverse direction, basically. Yeah. Okay, very nice. Any other questions, comments?
Yeah, maybe one question. You mentioned this result that for complex Banach spaces, the numerical index is greater or equal 1 divided by E.
Right.
And so is it complicated to construct an extreme example? Is it difficult to find a Banach space?
No, like when we are trying to construct in the first time, it might be difficult. But as I said, there is a paper by Duncan, Martin, and McGraw, and there is one more author. They constructed two-dimensional Banach space where the numerical index will be 1/.
Ah, okay, okay. I see. Okay, thank you.
Any other questions, comments? If not, let us thank the speaker, give her a big hand. Wonderful, wonderful talk. And Monica, can you share your slides with us, please?
Yes, sure. I'll leave it.
Okay. Okay, thank you everyone for being here. And maybe Stefan will announce the next talk next week if you have
Yes.
the information.
Okay. Also from my side, thank you very much for the very nice talk. It was very instructive and inspiring for looking into open problems.
Thank you.
And yeah, next week we will have an analytic number theory talk again by Liang-Yi Zhao, Professor Liang-Yi Zhao from UNSW in Sydney. He will talk about L functions again. Okay,
So
I will send out the announcement this weekend.
So all of you are welcome to join. So, so we can end our session now if there are no questions. Thank you, Monica. Very, very nice.
Thank you.
Okay. Bye-bye.
Okay. Bye, everyone. Take care. Stay safe. Bye.